The first mechanism is the viscosity mechanism. This has been described more than 30 years ago and basically involves parts of the cell walls of the cereals that we use in animal feed dissolving in the intestinal tract. They dissolve and form large gels which actually slow down the diffusion of nutrients, substrates and enzymes and effectively delay digestion and absorption of nutrients. What this effectively means is that the diet is poorly digestible and the animal gets less value out of the diet that's being fed. When we feed an enzyme, what it does is breaks down these large, soluble, viscous polysaccharides into smaller and less innocuous products. As a result, viscosity is reduced significantly and diffusion is restored to normal values. This increases digestibility and the performance of the animal is brought back to normal. Viscosity is a big problem for grains such as wheat and barley and triticale, but we really don't see this as being a problem in corn-soy rations, where viscosity plays a very small part of the response that we see when we're using NSPA's enzymes. The cell wall mechanism relies on the fact that the cell walls of the cereals we feed our animals are manufactured or made of polysaccharides which cannot be broken down by the enzymes that the animal produces. These polysaccharides include xylan, beta-glucan and cellulose, and the enzymes needed to break these down simply are not produced by pigs or chickens. The idea then is that we supplement the diet with enzymes that can break down cellulose, xylan and beta-glucan, and as a result break these cell walls open and enable the digestive enzymes of the animal to gain access to any cells which have not been broken down in the milling or pelleting process. The problem with this mechanism is that when we look at how much enzyme is needed to break down these cell walls completely, and the time required to break down these cell walls completely, is in far excess of what we actually feed the animal. So for example, 100 times the concentration of enzyme that we use commercially is needed to break down cell walls in an in vitro setup, and 24 hours is required as well, as opposed to the 1 or 2 hours that is the time that the cell walls are resident in the gut of the animal. As a result, we really don't believe the cell wall mechanism plays much of a role even in a corn-soy diet where viscosity is not an issue either. The cell wall mechanism, therefore, should not be considered as a principal mechanism when looking at the role that NSPAses play in animal feed digestibility. And now we come to the third mechanism, the prebiotic mechanism. As a matter of fact, we like to say this is really a signaling mechanism, not a prebiotic mechanism. But what do we mean by this? When you feed an NSPAs, it'll break down fiber into smaller fragments and ultimately produce what are called oligosaccharides. These oligosaccharides are not digested by the animal, but can be fermented by bacteria inhabiting in the gut. The oligosaccharides that can be produced depend on the enzyme that you use. A beta-glucanase would produce gluco-oligosaccharides, and a xylanase, xylo-oligosaccharides, and a mannanase, mano-oligosaccharides, and so on and so on. In the work that we've done so far, we believe the most important by far are the xylo-oligosaccharides, and that's why we're focusing on xylanase in this video and why we're focusing on xylanases in our product portfolio. So what do I mean by signaling? Classically, when people talk about prebiotics, they talk about products which are fermented directly into short-chain fatty acids. We believe that whatever enzyme is used in animal feed, we are never producing significant oligosaccharides in quantity to generate the short-chain fatty acids that we see in the small intestine or in the large intestine. The reason is simply that the quantity of ZOS that our xylanase will produce is very small, and the effect that we see in older animals in terms of short-chain fatty acid concentration increases is very large. So this is what we mean by signaling. Effectively, what we believe is happening is that the ZOS, or the oligosaccharides that the xylanase is generating from the feed, are being picked up by bacteria that can themselves produce xylanase, and these ZOS are being used, if you like, as signals tell these bacteria to develop, to grow, and to produce their own xylanases in very large quantities. Eventually, and over a long period of time, these bacteria begin to dominate. Xylanase production in the large intestine of the pig and the chicken starts to increase dramatically, and we see far more efficient digestion of fiber as a result. This is one of the mechanisms by which we believe that the prebiotic effect or the signaling effect takes hold. By increasing the microbiome's ability to digest xylan, effectively what we're doing is increasing the concentration of the short-chain fatty acids effectively in the ceca and in the colon of the pig. This has a knock-on effect. Some of the short-chain fatty acids that are produced as a result of these xylanase-produced signals, butyrate in particular, start a cascade of responses where endocrine products are produced in the large intestine, feed back to the stomach, and enable the pig or the chicken to hold on to feed much longer in that part of the digestive tract. So effectively what we're saying is the xylanase is changing the microbiome, changing the concentrations of short-chain fatty acids in the large intestine, and these short-chain fatty acids are feeding back to the stomach and telling the stomach to slow down and don't release feed into the small intestine. This results in a significant improvement in protein digestion. So let's recap the three mechanisms that I've just described. The first one, viscosity. It's not really relevant for corn-soy diets. It may be relevant if you're thinking of using wheat or barley. The second mechanism, the cell wall mechanism, for the reasons I described earlier, we really don't believe is a valid mechanism for the use of any kind of NSPAs, whether it's a complex enzyme or a simple xylanase. The third mechanism, the prebiotic mechanism, which we're now calling a signaling mechanism, again for the reasons we described, is a mechanism which we think dominates, particularly in corn-soy diets where the viscosity mechanism just does not apply. This signaling mechanism is of value because it tells you that an enzyme which can produce the xylo-oligosaccharides, and it is xylo-oligosaccharides we're looking for, will eventually improve the ability of the microbiome to digest the most undigested fiber in your diet, and that is the arabinoxylan fraction. This gives far greater benefits in terms of energy and signaling back to the stomach or the gizzard, as described previously. As a result, we believe that feeding the right xylanase that can produce the right signals will give you the best response in commercial feed today.